Hey, thank you for the nice introduction and the invitation. It is a great pleasure to present my work on dark matter superfluidity. And the talk will be based on a collection of works done in collaboration with mainly with Justin Corey and some other people that are listed here. Okay, so I'll begin by saying a few trivial statements that I'm sure you've already heard multiple times during this conference. Historically, the first robust evidence for the existence of the dark matter, as we all know, came from rotation curves, which rotation curves representing the functional dependence of the circular velocity of visible matter around the center of the galaxy as a function of the distance from the center. And in the standard cosmological model, again, as we all know, the dark matter is introduced as a collection of collisionless particles, and it is fascinating that these properties alone, just having additional component, which is collisionless massive particles, basically, is sufficient to fit various observations on different scales with the remarkable precision. Now, as you probably have heard, depending on which scales we look at, there are certain puzzles that is being discussed, and I would like to touch upon this. So we know that on cosmological scales, all we really know about dark matter is that it is a non-relativistic fluid with a corresponding equation of state, which is much smaller than 1. And that is all we really need to fit cosmological scale observables. Now, when it comes to galactic scales, then there are some small puzzles that still is being debated whether standard cold dark matter paradigm can accommodate. Which I would like to touch upon. Now, if we take these collisionless particles and study the structure formation within this model, to understand what kind of structure it creates, we need to do numerical simulation. And n-body simulations, which was first done by Navarro, Frank, and White, revealed that there is a more relatively universal density profile that dark matter particles tend to virialize into, which is called NFW profile. And it is a 2-parameter family of density distributions set by parameters ρs and rs. And what is interesting, and of course, the galaxy is divisible. The disk is hosted within these halos, right? As we all know. And what is interesting about this density profile is that it has a so-called Caspi core. So the density profile near the center, it goes as 1/r. That is argued that is not what observations seem to indicate. And there are few puzzles associated with this. With this deepness of the potential well in the core of the galaxy, of halos. So one of the puzzle is, I'm sure you've heard about, is the missing satellite problem, and which is connected also to big to fail problem. And the essence is that cold dark matter paradigm simulations, so standard model simulations, seem to predict that Milky Way-like halo, for instance, should have certain subhalos within the halo, which we have not seen. And the question is why? Well, one of the arguments for this is that the reason why we don't see them is not because they are not there. They are there, but they don't host visible matter, so that we don't see them. However, if the density profile of these subhalos is as Caspi as the NFW profile, but on different scale, then the potential well should be deep enough for these subhalos, at least in the mass range that is predicted by simulations, that they should be able to retain the visible matter, and they shouldn't be able to lose it so easily. Okay. There are some other issues that is being discussed. By the way, I'm not calling them problems because these statements depend on many different aspects of both observational and simulation. So, and which we're gonna point out throughout the talk. So another point associated with this cuspiness of this density profile of halo is connected to the dynamical friction. So as you know, dynamical friction is friction. So the drag force experienced by baryons like stars moving through dark matter, despite the fact that they are not directly interacting collisionally, they are not colliding with dark matter, but because they interact gravitationally, as object moves through the halo, it creates overdensities. And then once it outruns its own wake, so to say, then there is a gravitational drag force that slows it down. And this is called dynamical friction. And the claims that one encounters in the literature from people who analyze the predictions of CDM and observations, they seem to indicate that there is a certain minor puzzle about the dynamical friction predicted by CDM and relative to the observed one. There are few places where one could encounter this excess dynamical friction. So one is the rotation of galactic bars. So it is claimed that galactic bars should be slowing down more than they appear to be if the density profile of the halo were given by NFW profile that I gave on the previous slide. But these bars are not seem to be slowing down. So the resolution, the most vanilla resolution would be to somehow come up with a mechanism or understanding within CDM that the density distribution is not as big as CDM seems to predict. Another point is connected to the abundance of barred galaxies, which is also sensitive to how much dark matter you have in the central regions of the and throughout the halo. CDM. There are some claims stating that CDM seems to overpredict the galaxy merger rate. So in the absence of dark matter, so the encounters between galaxies that would proceed without the merger in the absence of dark matter, they are expected to merge if these galaxies are submerged within this extended halo, because when the halos overlap, that causes friction and they slow down. The halos are slowing down. As a result, these galaxies get attracted to each other more easily with larger impact parameters. And the point is that the increase in the merger rate would also mess with the abundance of the barred galaxies versus galaxies that don't have bars but have bulges instead. There is also another system. It's called Fornax dwarf spheroidal galaxy, which has a satellite that is few globular clusters orbiting this dwarf spheroidal, and if the density profile were given by the NFW profile for dark matter, then these globular clusters should be slowing down and sinking towards the center, which doesn't seem to be the case. So again, there seems to be some indication that it might be better if one can suppress the depth of the gravitational, the amount of dark matter you have near the core of halos. Okay, so one.
Excuse me.
So yes.
Yeah, just a clarification. Are you saying that CDM over-predicts the abundance of barred galaxies or under-predicts it? I couldn't catch that.
So my understanding is that in CDM you have more mergers, so you don't. So in CDM you have CDM predicts more bulgy galaxies than barred galaxies. So you don't get in simulations, or you don't expect to have as many barred galaxies as you observe. So it under predicts barred galaxies. I think, yeah, that's, yeah.
And on the previous slide, what was the point about the subhalos, that we don't see enough subhalo? I mean, we don't see enough satellite galaxies. Is that the point?
Yes, that's yeah. That this the famous missing satellite problem, that we don't see these subhalos that is predicted by CDM, and the question is why. And usually the argument is that because they don't have anything visible in it. And then the question arises, why? And depending on how much dark matter they have, these subhalos, then they could retain the visible stuff versus losing them with a different rate. But these are all, to my understanding, super minor puzzles, which I also don't feel, so to say, expert enough to talk about in details, because they are based on many different aspects of both observational and simulational. So I just wanted to point out in passing these points. Yeah. So what I find particularly fascinating, though, is the so-called diversity of rotation curves. So both simulations and in CDM and observations, they seem to demonstrate that that rotation curves among all the different galaxies that we observe and simulate, they show plenitude of diversity, so to say. So the shapes of the rotation curves are very different. Some of them are rising sharply, some of them are rising relatively more shallow way, etc. So the shapes are diverse. However, if we only look at galaxies with the same asymptotic velocity, which is same velocity that the rotation curve asymptotes to, okay, we only select those galaxies, then observation still shows the diversity of the shapes of the rotation curve. So as you see from here, these are the four galaxies with similar asymptotic velocities. However, this observed rotation curve, which is given by these data points, they are different. So, for instance, in here, the rise is quite sharp, while in this galaxy, this is a low surface brightness galaxy, the rotation curve seems to rise almost linearly, so very, very slowly. So what is puzzling is that although CDM simulations do show the diversity of rotation curves overall, when constrained to galaxies with a similar asymptotic velocity, then the diversity goes away. As you can see from here. Here, these bands indicate the simulation, so of simulated galaxies, while these data points are data for rotation curves. And the question is, what is responsible for this difference? Now, in these simulations, what has been done is that it's dark matter is simulated as an n-Barry simulation, as usual, and galaxy, so visible stuff is simulated by hydrodynamics. So this is simply two coupled substances. One follows the n-Barry simulation, the other one is hydrodynamics, and they talk to each other by gravity. Okay, so in other words, it seems that in different galaxies, there is some new ingredient that we need to introduce in order to understand what we see. And the question is, and turns out that the galaxies that are hardest to fit, for instance, this last one here. So obviously, based on this, it seems that compared to this simple simulation, we have to introduce additional effect more in this galaxy than the others, for instance, than this one, for instance. So usually these additional effects that are not captured by the simple simulation that I just mentioned are the so-called baryonic feedback processes, which is, so baryonic physics is quite complicated. There are complicated processes going on there. There are supernova, active galactic nuclei, etc., that could disrupt the distribution of dark matter within these galaxies. So the point is that we don't really know what was the formation history of the galaxy, of an actual observed galaxy. And depending on how much supernova activity they had, etc., they could deviate from the simulation, from the simplified simulation that is being done, more or less. But the problem is that the galaxies that seem to require more additional input, they are the low surface brightness galaxies. They are not expected to have had that many stars to begin with. So they are gas-dominated galaxies, and they are not believed. They are believed, at least based on the current understanding, is that they should not have had that many supernova activity, for instance. So the question is, how come that they look so different than from the simple simulation that excludes all these feedbacks? Okay. So now going back to rotation curves, which is also this, is that by analyzing these rotation curves, there is an empirical relation that is being observed, that was first proposed by Milgrom as a modification of gravity. I will say a few words on that. But the point is that the acceleration of this visible stuff, circular acceleration of baryons, as a function of the distance, seem to be tightly correlated with how baryons are distributed. So this is, from first glance, it may sound puzzling because we understand that main driving force for dynamics it should be dark matter, at least in most of the region in some cases, and dark matter distribution. And then the question is, dark matter distribution could be correlated with baryonic distribution somewhat because they talk via gravity. Okay. However, it seems, as demonstrated by this plot, that this conversation that the dark matter and baryons have only purely by gravity, okay, excluding all these additional feedback effects, is not sufficient to produce the tight correlation that is simply being observed in data. Okay, so this is simply an empirical relation, and it simply says that for small enough accelerations. So for large accelerations, the acceleration is the way we would expect to be in Newtonian gravity without dark matter. So at short distances, we also know that that the rotation curves are mainly governed by baryons, because baryons seem to be more compactly packed, so they dominate in the center of the galaxy. As we go out to larger and larger distances, then in CDM we know that dark matter takes over, obviously, because the rotation curve without dark matter would just drop. And empirically, it seems that the effect, whatever drives dynamics at large distances where baryonic Newtonian acceleration is negligible, can be approximated in this way, by this introducing the additional parameter A0, which ends up being comparable to the Hubble constant, to the Hubble acceleration. Okay, so now this is simply an empirical relation, and the question is, what is responsible for this empirical relation? So here also all these rotation curves would be nicely fit by some relation of this sort. Of course, now I'm here giving the simplified version. It's not all roses for this type of empirical relations. I mean, people have been considering different interpolating functions between two regimes. But okay, the bottom line, given all the uncertainty in the data, etc., I believe that the general effect is that at high enough accelerations, this acceleration driven by dark sector seems to be just one given by baryonic acceleration, so acceleration driven by baryons only gravitationally. However, at lower accelerations, there is this effect that this dark sector behaves in a way that generates acceleration that is given by this. Okay, and the question is, what is responsible for this, and what is the origin story of this empirical correlation? Because I mean, I don't know. I believe nobody really doubts that there is this empirical relation. So first is that the question is how we accommodate it in standard cosmological model, and we already discussed that we need to adjust baryonic feedback appropriately, which is perfectly, yes?
Yeah, can I ask a question? Yeah, can you
Yes.
go to the previous slide?
Yes.
Yeah, so just to be clear, so this Milgram's law, this A of R, this is just the centripetal acceleration, right?
Yes.
So Milgram's
yes,
law at the end of the day is just a statement about rotational
Spiral
velocities.
Yes.
Okay. Yeah, thanks.
Yes. Yeah. Thanks. Yeah. Thanks a lot. Yeah. Please feel free. Any questions are extremely welcome. Yes. Yeah. I must say yes that this it should be emphasized that this relation is only works in these galaxies. So in elliptical galaxies, you have different kind of observations, but things are messier. So it's not as clear cut as in these galaxies. Okay, so accommodating that, so that relation or the correlation by baryonic feedback sounds okay. It's perfectly reasonable, because until we really understand what is really going on there, right? And then I mean, these simulations are improving daily, so we just have to sit and wait. But the fact that there are these puzzles about certain type of galaxies that we don't expect to, we don't really know why we should expect more feedback require more feedback. Okay, this sounds to me interesting enough to think about whether there is something else that maybe it can be an indication of some interesting physics that could be hiding in this observation. Also, it must be noted that these low surface brightness galaxies that are harder to fit and require more feedback, like for instance this one with the CDM, they were actually discovered after this empirical relation was established. And people simply wanted to understand whether this empirical relation now could be invalidated by this precise measurement of these low surface brightness galaxies. But turns out that they also follow this relation, which is interesting. Okay, another dramatic alternative, as I'm sure you've all heard about, is the modified gravity. So people have asked whether you could replace the existence of dark matter, or at least most of it, by simply modifying gravity. Okay, so this was the original motivation for Milgram as well. So his point was and is that this observation of this empirical relation is an indication there is this new modified gravity, and in principle we don't even need to have dark matter whatsoever. Okay, and another third option is that maybe this observation is an indication of some interesting dark matter properties. So maybe these observations about the diversity and etc. and the correlation between two sectors, maybe it's an indication that there is some new physics in dark matter that we are getting a glimpse of. Because the fact that we can fit so many things so well with simply collisionless massive particles, it does not only speak highly about how successful is the idea, but how little we know about what dark matter does. So maybe this type of observations are glimpses of what might be there. Okay, so just as a fun historic fact, so the battle between modified gravity and hidden matter is not new. So one of the first attempts to, one of the first appearances that I'm aware of goes back to 19th century. The French mathematician Leverrier, who had predicted the existence of planet Neptune based on analyzing the orbit of Uranus. Later, he decided to analyze Mercury perihelion. And he realized that just taking into account all the celestial objects that he was aware of, he could not make sense of the motion of Mercury. So he postulated the existence of a new planet called Vulcan, the presence of which in the solar system could, in principle, explain the motion of orbit of Mercury. Now, as we know, this planet was never discovered because it's not there. And later, this perihelion was explained by Einstein's theory of gravity. So in some sense, modified gravity took over the hidden matter explanation of the puzzle. However, this does not seem that I'm trying to argue that we have to think in the direction of modified gravity, because dark matter, taking all the evidence into account, seems to be here to stay, because it seems impossible to get away without having dark matter. Okay? So my personal opinion, which is not just an opinion, but also based on many different aspects of my understanding of how fundamental laws of nature work, this modified gravity option seems to be less likely. Now, sometimes you may hear that the reason why certain sub-communities prefer this idea is because they think they argue at least that it is more minimal, because instead of why should we introduce new matter, new ingredients, new content to this, additional content to the standard model of particle physics, if we can simply modify laws of gravity. But the point is that modification of gravity is not such an innocent act as it was in 19th century, because before general relativity, before we understood how everything around us that we can explain falls in the framework of field theory and also quantum field theory. So for us, laws of gravity were simply F as a function of R. And in principle, we could have modified it, right? So we could have said, okay, why this and why not the other? Maybe observation indicates that it's not just this, but it's something else. But the point is that now the way we understand how gravity works is that the only way to modify gravity is to introduce new particles and new degrees of freedom. And that is not minimal. Actually, that's opposite of minimal. It usually tends to be quite challenging, because the moment we modify gravity, then we have to ask so many other questions and address it that it becomes completely untractable. So up to today, there is not a single proposal for replacing dark matter with modified gravity, which could actually compute tractably the predictions, analyze stability of the model, and still be consistent with observations. Okay? So I'm gonna try, since I'm incapable of studying baryonic processes in the CDM numerically, I'm gonna go with the third way and try to ask the question, and this is the question we've been investigating, whether we could think of some new features of dark matter that would explain some short-scale behavior or ameliorate some of the puzzles. And the question I would like to discuss is the idea of dark matter superfluidity. And dark matter superfluidity is not something extremely complicated. It is simply a mix between self-interacting dark matter and ultralight Bose-Einstein condensate dark matter scenarios. So self-interacting dark matter scenario proposes to bless dark matter with certain self-interactions that is not present in standard model, because standard cosmological model, because it doesn't seem necessary for cosmological purposes. But the original proposal by Steinhardt and Spergel, forgot the reference here, was that the self-interactions in the central regions of the galaxies could, because of the scattering of the particles, could lead to the fuzz out of the core and lift this cuspy core puzzle. Another direction is this ultralight Bose-Einstein condensate dark matter that I'm sure you already heard during this conference, which deals with the ultralight dark matter particles that would have the Broglie wavelength in galaxies of order of kiloparsec, okay? Which also tends to fuzz out the central regions of galaxies. And the superfluid dark matter is right in the middle of these two. And it is motivated by two following points. So for us, the way me and my collaborator, Justin Corey, we started thinking about this was because of the possibility of having environmentally emergent long-range interactions within galaxies, which I will talk about. Another motivation is the superfluidity itself, which was the motivation for Jeremy Goodman back in year 2000. And another motivation for Goodman was that in self-interacting dark matter, usually you need strong interactions. And then the question is, these interactions, whether they could lead to the gravothermal collapse of the core of the halo. The point is that because of the interactions, the core could start losing particles, evaporating, basically, kicking energetic particles cooling down as a result, lowering velocity dispersion, and correspondingly then collapsing gravitationally. What happens in superfluid case instead is that you already start with as cool as imaginable substance, which is sustained by the interaction pressure of the degenerate substance, degenerate particles. Okay, so what is superfluidity? Superfluid itself is the simplest possible fluid one can imagine. What is complicated is the formation history and the origin story of it, because it usually takes place through quantum phase transition for certain type of particles. But the substance itself is very simple. And there is one characteristic that determines the superfluidity. And it is the following, that the only low energy excitations that one has there are sound waves, nothing else. As a result, for some perturber moving through the superfluid, for it to dissipate energy, the only option is to radiate sound waves. But then for inertial motions that are subsonic, it is impossible, just like Cherenkov radiation only kicks in once you hit the barrier. Okay, so as a result, if a perturber is moving inertially with a subsonic velocity, there is no dissipation, because the only accessible channel for dissipation, which are these phonons with this dispersion relation, the sound wave dispersion relation, are kinematically prohibited to be radiated. Okay, so now you can ask, okay, so just to clarify, so in the air, we also have sound waves. We hit the sound barrier as we go supersonic, but the point is that it's not a superfluid. And why? Because once we hit the sound barrier, that's an additional friction we encounter. But when we are moving subsonically, we can excite other degrees of freedom besides sound waves that are transverse degrees of freedom. And that is what distinguishes air, for instance, from the superfluid. In the superfluid, you don't have other dissipative excitations. You only have sound waves, and that's the main feature that we need to concern ourselves, at least for the purposes of this talk. Now, the way we arrived at the superfluidity was we were thinking about how to have environmentally emergent Milgrom's law within galaxies. And we were thinking that the sound waves in superfluid, which are massless excitations, right? They're waves, sound waves. They could, in principle, mediate long-range forces if baryons, for instance, could exchange them. Moreover, one can realize that the equation of motion of these phonons of the superfluid in general takes some form of this sort in the stationary limit. So here P is an arbitrary function that is usually determined by the properties of the superfluid, in particular by the equation of state. So by having different superfluids, you would just have different equation of this form for the phonon. And the idea was that if one could use this phonon to mediate long-range force. So this is the left-hand side. This is what one gets in superfluids in general. And depending on which superfluid, there will be a different function P here. And the idea was that to couple this phonon to be sourced by the baryons. And in that case, maybe we could have some interesting phenomenology. And just to contrast, this phi basically plays the same role here as the Coulomb potential in electromagnetism. And naively, okay, so in electromagnetism, this first diagram is the only diagram that mediates the force between the source and some probe particle, right? So which is just an exchange of a photon, and it would be a Coulomb potential. This probe particle will be moving in a Coulomb potential. Now, because in case of a generic superfluid, you have a nonlinear equation of motion, in terms of diagrammatically translates into some schematically, these are just schematic diagrams of this form. And then depending on the level of nonlinearity, you could have different contributions. So in principle, the force law doesn't need to be 1/r, it could be more general. Okay. So, and once again, as I said, this P is given by the equation of state. Now, it turns out that it was possible to construct phenomenologically this theory of superfluid theory to argue what kind of properties it should have in order to have interesting observational consequences. However, to make everything self-consistent together with the microscopic formulation, that is proven to be challenging. So it's still missing. And the reason, one of the reasons because behind this, so to say, trouble is in the fact that zero temperature superfluid doesn't seem to be sufficient to give rise to this observed strong correlations that I was discussing in previous slides, because of the stability issues. It could give you nice the force law is a classical solution, but once you study fluctuations around those force lines, they are either superluminal or are destabilized. So that's an indication that it cannot be embedded into a reasonable microscopic theory of dark matter. So for us, the only way around of these stability issues was to argue finite temperature effects to be significant, which makes the effective theory even more complicated. And I personally don't have much of a handle on how to derive from a concrete microscopic theory the low energy finite temperature effective theory that we need to. So this direction, this is where it is at the moment. So unfortunately, there hasn't been much progress beyond the original proposal that we had, that it seemed like a sound idea and could be interesting for observations, but there is no connection between microscopic model and the effective theory that seems to work observationally. Now, you could ask that in general, maybe, but what if emergent long-range interactions don't even make sense altogether, right? But the point is that actually you can find a very nice example where it works. And this is it. So consider theory of two particles, these blue particles, blue dots, and the black dots. And this blue is an analog of dark matter, and these black ones are baryons. Okay, and imagine that the only interactions that we have in the theory are collisional interactions. So both particles are massive, both species are massive, and they only have collisional interactions. Okay, so then two baryonic particles could interact, and the effective potential could be computed. but they would have to exchange this massive particle, this massive loop of these other particles. And this doesn't change even if you have a lot of them around. So, and the reason why you have to propagate massive gapped virtual particles, this leads to the Yukawa suppression of the force, which is given by the mass gap of the particle, of the virtual particle you are exchanging. So if in the regime, when you have gas of these dark matter particles in the disordered phase, so just like in a gas form, if you bring two baryonic particles within, they would never experience long-range interaction. There would be a Yukawa suppression of the effective potential between them. However, it is extremely straightforward to show that if you cool down the system so that these dark matter particles, instead of behaving like a gas, they undergo Bose-Einstein condensation, so you go below critical temperature, then the effective potential becomes Coulomb-like. And two baryons, they are feeling long-range 1 over r squared force between them. And to understand it, one way to understand it is the following, that so to exchange a non-existing massive particle, you have to provide the level of off-shellness in the virtual particle is given by the mass gap, because the particle is not there. And the fact that you have gas around you, it does not help, because you don't have statistically particles may not have it in the immediate vicinity at all times, because sometimes you may be hit by a particle and sometimes not. This can be, of course, formalized in more details and has been computed by Ferrer and Grifols for the first time, showing that if you just have gas of particles in a non-condensed phase, you only have a Yukawa interaction. However, once you cool it down and you have Bose-Einstein condensation, then these particles, these particles of the gas, they are everywhere. So you have access to particles because their position is degenerate over the wavelength scales, and if they are in zero momentum state, then they are everywhere throughout your box. So then you don't, the level of off-shellness for the intermediate particles is not given by the gap, but is set by the virtual kinetic energy you have to provide. So this is just a rough explanation. So what happens is that these baryons can borrow a particle from the condensate, send it to another one, and the other guy will deposit it back to the condensate. And because these condensate particles are everywhere to begin with, there is nothing that has changed whether who borrowed and who returned. Okay. Now, more a physical picture is that in this theory, despite the fact that you have collisional interactions, if you introduce a baryon, it creates certain underdensity or overdensity, depending on whether interaction is attractive or repulsive, in the dark matter distribution. So in the absence of the source, if you would have homogeneous dark matter distribution, once you introduce it, it creates this overdensity or underdensity. And the other probe particle can fill this overdensity and underdensity. And the point is that when the particles form the condensate, particles are not dislocated only in the immediate vicinity. There is this 1 over r Coulomb-like potential shape distortion in the density distribution, which can be shown straightforwardly. Okay, this is a bit technical slide, which I'm not going to stop at, but okay. Now the point. So now there is this nice simple model in which you can write down where you have massive dark matter particles, scalar particles interacting with baryons, and they can mediate this 1 over r force. And we've shown that actually there is a parameter space, especially if you go in the fast dark matter direction, where this force, this emergent long-range force, could in fact compete with gravity. However, needs to be more work done to understand whether phenomenologically this is relevant or interesting. So all we really demonstrate is that there is a parameter space where for fuzzy dark matter-like particles in that mass range, that's important, that you could have these long-range interactions that could be gravity competing. But it has not been analyzed sufficiently to claim that it's a viable and interesting phenomenologically. Okay. Now, so far we just discussed the long-range interactions, but we can ask, but we have to form the superfluid. So how can one form a superfluid in the galaxy? Okay, so we can begin by standard NFW distribution of these massive particles and ask the question. So this is of course simplified approach, because in reality, everything's going to be taking place together, the formation of the superfluid and the virialization. However, we can ask if the profile started similar to NFW, under what conditions would we undergo the phase transition in this picture? And to form the superfluid, we need to fulfill two criteria. One is that particles need to thermalize. This is different from what we do in case of fuzzy dark matter, for instance, because fuzzy dark matter particles already have de Broglie wavelength for galactic velocities that is super long, it's kiloparsec. But if we are interested in forming Bose-Einstein condensate for particles whose de Broglie wavelengths can be significantly shorter, then we have to force them into lower momentum states than they are. And for that, we can achieve it in the following way, which is through thermalization. And if in the thermalized state, particles happen to be at lower temperature than the critical temperature, which is another way of saying it's degenerate, then they would form Bose-Einstein condensate. So the point is that if we have particles with the thermalized particles that on average are expected classically to have de Broglie wavelengths that are significantly overlapping, then quantum statistics forces them to occupy the lowest available momentum state. And it turns out that, there is a reasonable parameter space for cross-section and the mass for which you could have significant parts of the halo. Yes, of course.
So could you please repeat how this is different from an ultralight boson case? You said in fuzzy dark matter.
Yes. Yes. So the idea in fuzzy dark matter is that they don't even interact. So you don't have thermalization, and you simply have particles with de Broglie wavelengths that are super long, right? So kiloparsec. Also, so all the particles, they are extremely overlapping. At all times, and you don't need any phase transition to argue that. So on average, so in any given volume, if you look at in a region that is smaller than the de Broglie wavelength of this particle, which is a kiloparsec, it looks like a condensate because you just have super long wavelength particles overlapping with each other. Here, what we are trying to, yes.
Thank you.
Yeah. So here, what we want to understand is in the parameter space where that is not the case, because at large distances, if one could have CDM-like distribution and a mass range that is more close to electron volt than the fuzzy dark matter, we want to understand whether we can force condensation by some other mechanisms. Okay, so then we can ask the following question. If particles have certain interaction cross-section and a certain mass, what is the size of the region within which they can interact strong enough for them to thermalize? And it's easy to formulate the result in this way. So whether the thermalization radius is bigger or smaller than 30 kiloparsecs, it is equivalent to this constraint on the parameters of the theory. Okay, so the cross section and the mass. Important point here is that this is only possible if particles are highly degenerate in most of the galaxy, which is important because the interaction rate in that case, gets additional bosonic enhancement factor, which are technicalities and no reason to go into at the moment. But the idea is that the relation between interaction rate and the cross section gets additional boost by the degeneracy factor for degenerate bosons. And the idea is that if the phase space, imagine a gas of particles with highly degenerate phase space, and when the particles are interacting, if the final state in which particles scatter is already occupied by bosons, by identical bosons, then you get additional attraction towards the state because you get additional enhancement factor because of the creation operator acting on, or annihilation operator acting on that state. Okay, so this is very important, which I will come to shortly. It has interesting consequences that initially we did not realize, and only later we thought about. So final, so to say, to some point, final image that we had in our mind was that you would have the halo, certain central region that depends on parameters of the theory would thermalize and form a superfluid core, and it would be surrounded by the envelope of normal CDM-like distribution NFW tail of the halo. And this was interesting because then we could think of if we could make this idea of emergent long-range forces realize, we could think of baryons. So this is these black particles are baryons. A probe particle within the superfluid core interacting with of course the central baryonic distribution, as well as dark matter, because we have dark matter, through gravitational interaction, so by the exchange of graviton, which is this wiggly line, as well as by the exchange of the phonon of the superfluid, because superfluid would provide us with a large coherence, long-range coherence. However, if we would consider this probe particle moving outside of the superfluid core, then the only interaction between baryons and dark matter would be through gravity. Okay, which could have interesting consequences. But okay, it turns out that yeah. So the issue with these emergent long-range interactions is that it is in one direction that I talked about. It is hard. The one that was initially proposed by us to account for Milgrom's empirical relation is that it is really hard to connect that effective field theory with the concrete microscopic model. Although it does tell us something about what should be the properties of the particles. For instance, Milgrom's law seems to prefer three-body interactions. So the equation of state to be for the superfluid to be polytropic equation of state, that with the pressure being proportional to density Q instead of pressure proportional to density square, which is for two-body interacting massive particles. However, precise connection is still missing. So that direction is still somewhat up in the air. Another direction, which was this toy example that I considered, in which for fuzzy dark matter mass range, one could mediate Coulomb-like force. That direction requires more phenomenological analysis. There is no other question but to analyze just what kind of phenomenology it gives. So let me skip this. So there is a small caveat, which is not so small, and it is connected to this question of efficient thermalization, because as I discussed, it was vital to have galactic scale superfluid core, galactic scale thermalized core. One had to argue, one had to use Bose enhancement factor to boost the interaction rates. Otherwise, it is impossible. However, then this kind of raises a question whether we should use the same enhancement factor in the bullet cluster bound. Okay, so this is the question. So on the one hand, we need to boost the interactions in this overpopulated, in this limit of overpopulated phase space with the high Bose enhancement factor. However, then the question is, when we consider bullet cluster, then is the bullet cluster interaction also boosted by the same factor, which was not taken into account before. So to put everything in some concrete context, so up to now, the best candidate, in my personal opinion, for the superfluid dark matter model is simply the original one, which is massive scalar real particles with lambda 5 self-interactions and repulsive. They must be repulsive, otherwise superfluid would be unstable, which is also a distinguishing fact from axion-like particles who have attractive interactions. If you were to expand the cosine potential, then the a to the 4 potential term would have the positive side, the opposite side. So these are attractive particles. Okay, so this is the original model proposed by Goodman. Then they claimed it to be ruled out, but it was based on some oversimplifying assumptions, and which we can get into later if you'd like to, but that simply also will become clear during what I'm gonna say. So it was ruled out, it was claimed, but our revised analysis showed that it's actually not, and the structure of the halo is actually more interesting than they thought, and I'll talk about it. Okay, so let's go back to bullet cluster. So for bullet cluster, what bullet cluster tells us constraints in reality is the interaction rate between particles. So usually then we convert this interaction rate to the cross-section bound. And because the most popular considered model is WIMP-like particles, and for WIMPs, the mass is super high, so that you can forget about the degeneracy factor of the interactions. And we just simply quote usually sigma over n had to be less than 1 centimeter square per gram. However, since for us in sub-electron volt mass range, and especially because for thermalization we had to strongly rely on this bosonic enhancement, which is huge factor, it needs to be also introduced here. If you have two, because all the velocities are of the same order, so virial velocities you have, so bullet cluster, yeah, maybe I should just state, I'm sure it was already mentioned, but so bullet cluster is believed to be a net result of the collision of two clusters. So one cluster literally went through another one, and as you see, so these lines represent the mass distribution within this cluster, and the light shows it's an X-ray, so it shows baryons basically. And as one can see, you see for baryons exactly what you would see: the development of shockwave front, etc. However, what is puzzling is that these mass peaks seem to be offset relative to the light, and this is puzzling because for undisturbed cluster you would expect these two centers to coincide. So it is believed that this is an indication that that dark matter interacts. So these dark matter particles from two clusters, they interacted with each other much quickly than the baryons did. Okay. Okay, so right. So in case of this ultralight mass range for m less than electron volt, the cross-section bound that we infer from these classic papers needs to be revisited, and it becomes much tighter, and it depends on the mass, and that is because bosonic enhancement factor also depends on the mass of the particle. Now, interestingly, so one gets the following generic picture that I'm going to explain now, which is you would have certain region outside of which particles have not scattered even once, so they are not aware of having any interaction. So their density distribution should be similar to NFW distribution. Now, then we have a region within which superfluid phase so thermalization and the phase transition took place. And by the way, this is not a simulation. This is just my personal artistic depiction of the situation. So now Within this thermalized region, then the superfluid phase transition take place. Now, these dots are denoting here there's some leftover particles that remained outside of the superfluid phase, and these bluish disks, they indicate the superfluid solitons that were formed. Now, whether you have a single soliton or many solitons in this thermalized region, it depends on what is the gene scale, okay, for this given set of interactions that these particles have. Just like when you form stars from a cloud, you form a cluster of stars. Here it's the same. So once you have phase transition, you would form a cluster of the superfluid solitons. And then depending on what's the hierarchy between the size of the thermalization region and the size of the soliton, you could form a different picture. You could either form just one or few. Now, gene scale simply follows from analyzing the dispersion relation around the homogeneous superfluid. So there is this gene instability, that this tachyonic gravitational mass that drives gene instability, and then this is the sound wave of the superfluid, and that gives us the characteristic momentum, which correspondingly translates to characteristic wavelength, beyond which the instability kicks in. So omega becomes imaginary for small enough k, and as a result, corresponding modes become unstable. Now, interestingly, the sound speed in this case of two-body interactions that I mentioned, which is the simplest case that can give you superfluidity, the sound speed squared is proportional to the density. Therefore, both terms here are proportional to density, and therefore the characteristic k for which this omega becomes imaginary is independent of the density because it drops out. Because gene scale is literally the solution of omega equals to 0 equation. And if both terms are proportional to rho, it is independent of rho. And converting that k into the gene's wavelength, which is just 2 pi divided by k, for which this vanishes, we get this following relation, which is interesting because it is simply determined by the intrinsic properties of theory. They are completely independent of the environmental properties, like a density of local density, etc. So it's simply given by the sigma and m. And what was for a while puzzling to us is that this enhanced bullet cluster bound was necessarily giving us a constraint, inevitably giving us constraint that was too constraining to get large superfluid solitons. So superfluid solitons were impossible to form, which were bigger than few kiloparsecs in diameter. So, okay. So because of this, we started thinking about a way around this puzzle. And it turns out that the only way you can evade this enhanced bullet cluster bound for sub-EV particles is to argue actually, so you go through the fire, basically, to argue that the entire halo must have undergone superfluid phase transition. And the phase, so to end up in the phase space that is not a phase space of overpopulated gas, which I'm going to discuss now briefly. I'm running out of time, I know, but yeah, feel free to cut me off anytime. I'll try to finish quickly. So the idea is that let's see what happens if the halos are completely thermalized. Okay, so if halos are completely thermalized, then in the absence of gravity, if you try to form the completely homogeneous superfluid, okay, would condense completely. For that, sigma over m has to be big, okay, it has to overshoot that bullet cluster bound and go beyond. And as a result, okay, the whole thing will be in a superfluid phase. However, then gene instability kicks in, and this would-be homogeneous superfluid in the absence of gravity would break into the superfluid islands. And one of the assumptions here is that because of this full thermalization, we need to have anything interesting to say about the outcome. We need to argue that significant fraction of the mass goes into superfluid phase and doesn't remain in the particle form, which is justified by the observation that effective temperatures, if we estimate, are many orders of magnitude smaller, and orders of magnitude smaller than critical temperature. So density profile of each soliton is given by this distribution. So it's a chord profile. So it's regular in the center. And the size is given by this, which we also talked about in the previous slide. And important point is to notice is that to realize is that by analyzing different parameter spaces, etc., the diameter of the solitons is inevitably much smaller than is smaller than virial radius because of phenomenological viability of the model. Okay, but if we now there is another effect after this that becomes important, which is the tidal disruptions, because these solitons generically tend to get tidally disrupted because of the collective gravitational effect of the halo. And the only ones that can survive is the central one and the ones that are too dense. They need to be at least 40 times denser than characteristic galactic density, which is 10 to the minus 20. So this rho galaxy, by rho galaxy, I mean 10 to the minus 25 gram per centimeter cube. But those need to form, therefore they need to initial over densities, the scale that it starts collapse from would have to be significantly bigger than L. So it has to start around twice L region, the region of the size of twice L, and collapse into size L. And that would most likely get disrupted until it becomes compact enough to withstand the tidal disruptions, because everything is happening at the same time. So our final result of this Gedanken simulation is that so you fully thermalize the halo, so you break it into solitons. There is a central soliton that survives, and it is surrounded by this virialized, stretched, spaghettified debris of superfluid solitons around it. That on average it will be virialized, and our best guess is that this distribution will be similar to NFW distribution, but the difference is that they are not in the particle form. These are virialized streams of the superfluid dark matter. So which could have some interesting implications phenomenologically, which we have not looked at yet. Now, mass of the central soliton obviously depends on the size in this way. L, it cannot be arbitrarily large because L is directly related to the equation of state of the fluid. And asking the question for this equation of state to be non-relativistic at matter radiation equality puts a constraint on how large L can be. So for instance, for L of order of 30 kiloparsecs, it's fine, it's 10 to the minus 2. For L equals to 50, that would be 0.1, that would be already borderline inconsistent with the non-relativistic, strongly non-relativistic equation of state. So L equals to 30 seems to be fine, and this is the interesting point that I'll say few words and then I'll finish. So the point is that also one important thing that I already said is that this L, it simply depends on the parameters of the theory. So it is given by lambda, which is a self-interaction coupling strength, M, which is the mass, and G is the Newton's constant. It's independent of the environment. Therefore, these cores, if they are really formed, you would expect them to have the same size in all galaxies, irrespective of the size of the galaxy and density of the galaxy, which is roughly the same anyway. Okay, which is interesting because although for Milky Way-like galaxies that they would be less interesting, but for dwarf galaxies, like low surface brightness galaxies that I started discussing with, which were a bit puzzling to fit with CDM, they are extremely interesting because in their case, just to remind you, the rotation curves would be completely surrounded by the superfluid core. So this these observations would be basically made within the cores, within the central core of these dwarf galaxies. If L is 30 kiloparsecs, L is the diameter, so the radius would be 15. Now, this is interesting because unlike CDM, superfluid core is not cuspy, it's a chord profile, and therefore it is more easily dominated by baryons. Therefore, baryonic, depending on how baryons are distributed in the core, they could affect, they could lead to the completely different shape of the rotation curves. For instance, these are two examples of toy galaxies with the same baryonic content, same total dark matter content. So same dark matter content within the central, same central soliton mass in both cases, forgetting about all the envelope, and the same baryonic content within the central soliton. The only difference is that in this toy galaxy on the left, the baryons are more cuspy, densely populated, densely distributed, and the other one is more homogeneous. So they are both approximated by the so-called spherical exponential profiles. In the first galaxy, the parameter, the length scale that sets after which the density drops exponentially is 1 kiloparsec, so it's very narrowly distributed. In the other one, it's 10 kiloparsecs. And you see that there is the shape of the rotation curves is dramatically different. And in fact, in the one case, which is expected, baryons dominate over the dark matter, while in the other one, the baryons are so shallowly distributed that they are always subdominant. Okay, so since I'm already running out of time, so now there is this parameter space, just say a couple of words. Okay, this region, so this is the parameter space for mass of the particle and sigma over m. And this green region corresponds to the parameter space when quantum pressure would be dominating over the interaction pressure, which is not the case that we are interested in, because that puts us in this fuzzy dark matter type of mass range. We are interested in pressure supported, so superfluid dark matter, which is pressure supported system. Then here, this is the one, this white region would be fine. So here, interaction rate is small enough for bullet cluster not to be an issue, including this enhanced, I'm talking about the enhanced bullet cluster bound for ultralight particles, not sigma over m order 1, which is here, but the enhanced one. As we are increasing cross-section for a given mass, we would reach this parameter region where now bullet cluster bound would be problematic, and then the question was, now is that where we stop, or there is another disconnected parameter space which would be actually okay with the bullet cluster constraint? And as I argued, if full thermalization takes place with a sufficiently small amount of leftover particles outside of the superfluid phase, then the bullet cluster bound in that case could be resorted back to the original one, which was sigma over m order 1. So as we are increasing cross-section, although at some point it becomes problematic for bullet cluster, if it's too big, then one can make the case that it's not inconsistent with bullet cluster, because you simply don't have particles in the gaseous form. You only have negligible fraction of them, and you have basically fluid, superfluid streams that are very weakly interacting because they don't have phase space enhancement in the final state of the scattering. Now this purple region is prohibited because at that point equation of state would become relativistic. And there is another region which is already, it's a weaker constraint, but if we have a real scalar field being a dark matter, there is a certain parameter space for which it could evaporate, simply because if you have a condensate which has only 2-to-2 scattering rate, you could still have, for instance, 4 particles from the condensate annihilate into 2 relativistic particles, and they would escape. and that would lead to the depletion of the core. And this constraint basically comes from asking for the lifetime of this superfluids to be of order of the Hubble time. And these lines, so the dotted line corresponds to gene scale or the size of the soliton, the diameter of the soliton being 0.1 kiloparsec. Dotted line is, the dashed line is 2 kiloparsec. So the size of the diameter of the soliton being 2 kiloparsec, and the solid line is 30 kiloparsec line. Okay, and this is what we think is the most interesting range of the parameter space, as long as we are not misled to argue that bullet cluster bound can be lifted. Okay, and since I'm out of time, I'll just leave the concluding remarks, and please, any questions are welcome. Thank you.
Okay, thank you, Lasha, for that nice overview. So any questions?
I have a question. In one of the slides, you showed the density profile, which is a sinc function.
Yes.
There,
Yes.
over here. So this is also the density profile for an ultralight boson in the Thomas Fermi regime. So is that
Yes.
the same as this?
It's the same. Yes.
It's the same.
Yes.
Okay, I see.
Yes, absolutely. Yeah, it's just a massive scalar with the lambda phi 4 interaction.
Yes.
Yes. Yeah.
And so
In fact, yeah.
yes, sir.
Go
Sorry,
ahead.
please continue.
No, it's okay. No. Please.
So here we don't have a soliton in the superfluid case. We don't have a soliton that is surrounded by an NFW envelope, right? The entire thing is a soliton. Is that what's happening?
Yeah. So the idea is that so this profile individually is an isolated self-sustained configuration, and of course, but the point is that how you form them, right? So usually you don't form them. If you start with the, so imagine the structure formation, the particles start coming together, densities are growing, right? So it is highly counterintuitive to expect the entire halo to, especially if it's thermalized, to just collapse into a single core instead of, because of perturbations, to break into the fragments, just like clusters of stars are being formed from the cloud.
Okay, so then here in this case, will there be, so in fuzzy dark matter, there is this core halo mass relation, right? So will there be something like this for these?
Can you remind me this core mass relation?
So these Shive et al. Simulations, they gave a power law relation between the mass of the soliton and mass of the surrounding halo.
Okay, so maybe, and exactly. So for that, one has to really study how these overdensities are growing, and which we have not done. Yeah.
Okay.
Yeah, but there should be something, because as I said, size is independent. So that's but the density, it depends. It depends what's the overdensity and what's the initial power spectrum of perturbations. Yeah, but there should be some relation like that. Yeah.
Thank you.
Yeah. So I have a question. So last week there was a paper that I think microlensing places some new constraints on superfluid dark matter. So can you show on that plot where do those constraints sit?
Who was the author, if you can remember?
I don't remember. I just remember reading the title that there was some.
Because there have been a number of papers in the past that study this long-range effect, and this our original idea, which is I feel the model is a bit premature to do this detailed phenomenological analysis for. But if it's about actually studying the substructure, yeah, I mean, I don't know, because we still don't understand properly what's the structure, so of the halo. So I don't know how to even do precise microlensing
Okay.
bit.
Yeah. All right.
Yeah.
Thanks.
Because you see, this is important because whenever a theories come up with some idea, and if some formula is produced at some point, sometimes it is viewed as already clear-cut prediction that you can test. I mean, sometimes yes, but the point is that in many cases, this can be only taken as some guideline of what could be qualitative picture, because the details are usually in these complicated models are much harder to work out. That's my personal take. Yeah, but I have not. I'm not familiar with the paper, but I'll try to look it up. It's interesting. Thanks.
I have a question about, are there galaxy formation simulations using this kind of superfluid dark matter? And do you know if it would lead to different predictions, for example, for number of satellite galaxies and things like that?
Yeah, I mean, that would be interesting to do. I've discussed with in past with colleagues, discuss what kind of simulations one could do. But the point is that I could never really understand how could one simulate this thermalization and phase transition at the same time, because there was this. We had this understanding that you had certain regions that are thermalized and there's other regions that are not. And it seemed a bit complicated, but right now I feel that one could in principle do this simulation, which is which would be simply, it would be an approximation, but just to use a polytropic approximation for the superfluid dark matter with a certain equation of state, which is p proportional to rho square. The only issue there is that it probably should allow for caustics, etc. So it has to be the simulation of this polytropic fluid that are allowed also to go through each other time to time. So that part I'm a bit fuzzy on, which is also something that I don't quite understand with fuzzy dark matter simulations, because when we treat it, when we describe fuzzy dark matter, which can be complete, on my account, complete misunderstanding of how things work. But when we describe the halo by certain single wave function as a function of time and space, we are writing down one function that determines the distribution of a lot of particles. So in principle, what prohibits me of having 10 different values for the velocity field in a single point, and whether that could be accounted for by simulation. So of course, one can average them out, but that always imposes certain precision. This is I never properly understand, but that's mainly because of my lack of education. So similar things need to be also addressed in the superfluid dark matter case. But if you forget that for a moment, then I would probably do it to simulate the polytropic gas, polytropic fluid. And it will be some kind of turbulent polytropic fluid. But I'm not aware of anybody doing it.
Thanks.
Hi. Are there any other observational consequences of this superfluidity? Like
so one interesting point could be the dynamical friction, because I jumped over this. So this idea that superfluids tend to suppress dynamical friction. So, but again, we've done some computations, so analytically we understood better. It was, for instance, believed that there are some discontinuities across the sound speed, and we showed that it's actually not the case. But phenomenologically, it has not been really properly worked out. So at least, so there are also results of older results, including by Ivo Stryker, that how accelerated sources dissipate energy in superfluid, because even if you don't expect dissipation for subsonic motion, you would expect it with accelerated motion, like Bremsstrahlung. But I don't know, what's the full kind of picture. I mean, at least myself, I haven't studied it, but that would be an interesting observational feature to try to have a concrete, more quantitative prediction when it comes to dynamical friction.
Pierre Sikivi and his collaborators for many years have been working with the axion and also doing something very similar in the sense that the axions thermalize through various interactions and then form a Bose condensate. They don't use the word superfluid, I think, and I don't think they call it a soliton, but isn't it the same thing? Of course, the potential is different.
Yeah, that's a good question. So that's the point. So axions cannot give you superfluid because it comes from this dispersion relation, basically. So what happens is that in case of repulsive interactions, which is the case for our what we are assuming, lambda being positive, the sound speed is squared is positive. So you have sound waves. So if you were to consider homogeneous distribution, there would be sound waves as long as you don't hit this, you don't get near this range, which is G scale, unstable region. In case of axions, because the sign of lambda is different, there are no stable sound waves. So that's why it cannot be the superfluid. So instead, what stabilizes the dispersion relation is the higher order K term. So here you have K to the 4 over m squared, 4m squared term, which is the kinetic energy of massive particle, and that's the stabilizing factor. But the interaction actually contributes to destabilization. So that's what happens with the attractive gases. It's a well-known phenomenon that if you consider BC, Bose-Einstein condensate of attractive particles, it's actually unstable and it forms these bright solitons. So it breaks into some solitons, which is a kind of a Ginsey instability, but instead of driven by the gravitational tachyonic mass, it is driven by the Bronstein sound speed term. So that's how these two things are different. Yeah.
Okay, but they also claim that they get around 30 kiloparsec or tens of kiloparsec condensate correlated over that.
Depends on the model. For fuzzy dark matter, you definitely, that's what you get up to few kiloparsecs, I guess. Maybe 10 is like, if you stretch it, but I don't see how, if you are near electron volt or a bit modestly below electron volt with axion case, unless interactions are literally zero and somehow you argue that, but you have to somehow make sure that your particles don't have the characteristic de Broglie wavelengths you expect them. Because let's think about it, right? So fuzzy dark matter particle has a de Broglie wavelengths, let's say 1 or 10 kiloparsecs, let's say, right? So now if I take 10 times heavier particle, right, it's gonna have, okay, let's take 10,000 times lighter, right? So let's take 10 to the minus 15 electron volt, right? For instance. Then the de Broglie wavelengths will be parsec, right? So in other words, you have particles with de Broglie wavelengths given by parsec, and you have a lot of them. They are not interacting efficiently to thermalize. If you were to arrange them in some homogeneous box, then of course, on average, they could behave like a condensate because they will be extremely overlapping. But in that case, with all these inhomogeneities in the halo, nothing is forcing them to actually go in the superfluid phase. So what you can say is that in certain regimes, it behaves like a Bose-Einstein condensate, which is fine because you look at some small part of the universe, for instance, for the axion experiments, right? So de Broglie wavelengths, you could have few meters mass range that they are interested in. De Broglie wavelengths of these axions can be few meters even. And now, if your apparatus is small enough compared to this, then on average, it will see like a condensate. But of course, as we are traveling through the fluid, it will see some overdensities and underdensities because some places are higher density, sometimes some are less. but it's not gonna be a self-sustained configuration, which is a result of the balance of gravity and pressure. Because in case of axions, pressure cannot stabilize the cloud. It's attractive, so it's gonna try to collapse it even further.
I see. Thank you.
Okay, thanks, Lasha, for thanks once again. And with that, we'll close today's session.